Good evening, everyone. Welcome to Boise State Physics First Friday Astronomy. My name is Heidi Wu. I am an assistant professor and astronomer in the physics department of Boise State. Before we get started, I have a few announcements. So today we are here ready to listen to Professor Yuan Li's talk, Turbulence in the Heavens. And next month, we will be hearing from Dr. Carl Schmidt talking about ionosphere and then plasma torus. In April, we will be hearing from Dr. Aaron Cox about how to build a planet. And so during this lecture, if you have questions, please use the chat feature on YouTube. So you need to log in and then put your questions here. And then I will be monitoring the questions and then relay them to the speakers. This evening, I'm very, very excited to be introducing Dr. Yuan Li from University of North Texas. Dr. Li receives her bachelor's degree from Nanjing University, master's degree from Purple Mountain Observatory, and PhD degree from Columbia University. She was a research fellow at University of Michigan, Flatiron Institute, and University of California, Berkeley. She joined the faculty at University of North Texas in 2020. Dr. Li is a world expert on the supermassive black holes in the universe. Her research has really helped astronomers understand how supermassive black holes shape galaxies and galaxy clusters in the universe. If that's not impressive enough, Dr. Li is also a world expert on simulating the turbulence in the universe, which she will tell us about. Turbulence is one of the most difficult research areas in physics. And Dr. Li has developed sophisticated simulations to help us better understand the impact of turbulence on galaxy formation and star formation. Dr. Li has recently won several prestigious grants from NASA for her outstanding research. Congratulations. Please join me in welcoming Dr. Yuan Li. I was still.
Thank you so much for the introduction. Shall I start sharing screen?
Yes, that'd be great.
I think I lost it. Okay. Is it working?
Great.
Okay, thank you. All right. So like Heidi said, I'll be talking about turbulence in the heavens. But first, we're going to start with turbulence on this planet. When I say turbulence, a lot of you might think of the turbulence you experience when you're on an airplane. And a lot of the times when they announce that you're experiencing turbulence and you look outside, you might not see anything. And that's just because we can't see air molecules. So we can't really see the motions, the turbulent motions of the air. And nobody is drawing these things in the air for us. But we can see clouds. And the clouds are oftentimes turbulent. And we can see the turbulent motion when there are other tracers in the air as well. So if you look at the smoke coming out of a volcano, it looks turbulent. You can also literally see turbulence in your backyard. If you have a grill and you look at the smoke coming out of your grill, that is turbulence. You also see turbulence when you blow out your candle and you look at the smoke out of the candle, or you look at the flames and the fire. That's also turbulence. And turbulence is not just in air or gas, it can also exist in liquid. So liquid and gas may look different in some ways, but they're both fluids. They both obey the same physical laws, and their motions can be described by the same set of equations. So you can pour milk into coffee and see the turbulent motion of milk. If you pour water into your teacup, you can see the turbulent motion traced by the tea leaves. So what really is turbulence? It's really hard to describe what turbulence is. In fact, we don't have a complete description of turbulence. It is, as Heidi said, it's one of the most difficult problems in physics. But if I ask you to describe what you see when you pour milk into coffee, you would probably say you see some whirls or twirls or swirls. And we physicists sometimes call them eddies. And they're also beautifully described in this drawing by Leonardo da Vinci. You see these bigger whirls and smaller whirls. A turbulent flow is usually made out of whirls of all different sizes. And as this beautiful poem describes, in a turbulent flow, big whirls have little whirls, which feed on their velocity. And little whirls have lesser whirls, and so on to viscosity. And I'll come back to viscosity in a little bit. So is everything turbulent then? Is every flow a turbulent flow? No. So here you're seeing turbulence, and you're seeing turbulence here in the smoke. But this part, when the milk just comes out of the milk cup, or when the smoke just comes out of the candle, it's not turbulent. You don't see whirls or twirls there. And these are called laminar flows. So they're sort of the opposite of turbulent flows. And one way to think about the difference between a laminar flow and a turbulent flow is the predictability. So if you look at this marching band on the right-hand side, which is sort of a laminar flow, you can predict where these people will be 5 seconds from now or 10 seconds from now. But if you look at kids on a playground and they're running everywhere in all different directions, you can't predict where each individual kid will be 5 seconds from now, 10 seconds from now. Turbulence is very much related to chaos and complex systems. So on the right-hand side, a laminar flow is very predictable. On the left-hand side, chaotic motions are impossible to predict. Now, I should mention that turbulent flows are irregular and chaotic, but chaotic or irregular motions are not necessarily turbulent motions, just like the motions of these kids on the playground are very much chaotic, but you're not looking at turbulence here. Mathematically, the fundamental reason for fluids to be able to develop turbulence is the nonlinearity of the Navier-Stokes equations, which describe the motions of fluids. And they're shown on the left-hand side. I'm not going to explain these to you, but just to show that these are rather complex and can give you headaches. But they're really just applying Newton's second law to fluids. They're basically F equals ma, but for fluids. And because of the nature of fluids, these equations become more complex and nonlinear, which can give you turbulence, one of the hardest questions in physics. And even physicists joke about this. And I like this joke. According to the internet, this was a joke made by Heisenberg. He said, when I meet God, I am going to ask him 2 questions: why relativity and why turbulence? I really believe he will have an answer for the first. Maybe it's not that funny to people who are not physicists, but I thought it was super funny. And it really tells you how hard even physicists think turbulence is. Now, even though we still don't have a complete description of turbulence, we have done many experiments to study turbulence, and we have figured out when a fluid can become turbulent. What we found out is that it's basically determined by a simple Reynolds number. And that Reynolds number is just the characteristic length scale of the fluid times the characteristic velocity of the fluid divided by the viscosity, or the stickiness of the fluid. Another way to think about this is it's just the ratio between the inertia force and the viscous force. And it's very intuitive. So if you have a flow that's slow or very viscous, then it tends to be laminar, like this top one. If you have a flow that's fast and not very viscous, then you have a larger Reynolds number, then the flow can become turbulent. And it's consistent with our intuition from just daily experience. So you can pour milk into coffee and generate turbulent flow there. But if you pour milk into honey, you won't get turbulence because honey is very sticky or very viscous. So it has a very small Reynolds number. It doesn't tend to develop turbulence. Now let's talk about heavens. We know that the universe is not filled with honey. And things tend to move very fast in the universe. For example, stars and galaxies can easily move at hundreds of kilometers per second, or if you like, hundreds of miles per second. Let that sink for a second. That's very fast. So in most astrophysical environments, the typical Reynolds numbers are larger than 1 million. Which makes essentially all astrophysical fluids turbulent. And we do see turbulence everywhere we look in the universe. So if we look at the surface of a planet, this is the surface of Jupiter. It's very turbulent. And the surface of stars, like our sun, is turbulent. And even though we can't see the interiors of stars, we are very sure that the interiors are also very turbulent. And the turbulent sun also sends out winds into space, just like all the other stars. And the wind from our sun is called solar wind. This wind is also turbulent, according to the data we have collected with space probes. And when this turbulent solar wind collides with the turbulent heliosphere above our turbulent atmosphere, then the 2 turbulent fluids collide together and create these beautiful aurora. And we also see turbulence in the outflows from supermassive black holes. And so this is the kind of stuff I do usually. So I work on black holes and black hole outflows. You're looking at the jets coming out of a very famous black hole, this black hole in the center of a galaxy called M87. And these are made out of relativistic particles that are moving very fast. And we're looking at the radio emission from these particles. And it's very similar to, I think, this picture of a candle. So I think we're basically looking at the turbulence smoke coming out of a space candle. Now, we can't really see our own galaxy like from the outside, but if we were able to take a picture of our own Milky Way, it would probably look kind of like this one. So we live in a disk galaxy. And when we look at the picture of a disk galaxy like this one, we might say, well, it looks beautiful and rather peaceful. So you might not think that you're looking at turbulence. But if you were to study the evolution of a galaxy like this on a computer, you run a simulation, you would realize that the galaxy is very dynamical and the gas within the galaxy is very turbulent because there's constantly streams coming in from outside of the galaxy, just like in this fountain, pouring more gas into the galaxy, stirring up what's already there and making it turbulent. And if we look carefully at the stuff in between stars called the interstellar medium, we do see all of these turbulent clouds. And we think that the interstellar medium is turbulent. And it's also very important that the interstellar medium is turbulent. We think that the turbulence in the interstellar medium is very important for galaxy evolution, and it's regulating star formation in galaxies. So we know that stars form out of dense cold clouds inside galaxies. So if we zoom in here, we might see something like that. And these little blobs are stars that are forming. So when we first started to study star formation, we added up all the forces and we realized that gravity always won. So stars should be forming very quickly and galaxies should use up all the gas very quickly, turning all the gas into stars. Instead, what we see is that all the galaxies in the universe are forming stars slowly, gradually, steadily. You can also say that they're forming stars very inefficiently. So it's like you have $100 and you go to the store, you come back with $90. For some reason, you don't spend all the money you have. For some reason, galaxies are not turning all of the gas into stars as quickly as we naively think they should. And then we realized, wait a minute, there could be extra pressure force from turbulent motions, which would prevent star formation or slow down star formation. And that's just like when you stir up your teacup, the tea leaves will start floating around instead of sinking to the bottom. When you stir up your chicken noodle soup, then the chicken and noodle won't sink to the bottom. So we think that turbulence is stirring up the gas inside a galaxy, preventing stars from forming too quickly. And now the question is, what is stirring up the stars? Oh, sorry, what is stirring up the gas then? Well, it turns out that stars themselves can provide a lot of stirring. So we're looking at a star forming region in the Carina Nebula. So if we zoom into there, we can see these jets coming out of newly formed stars. So very, very young stars tend to send out jets into the interstellar medium. And these jets carry some amount of energy. And that can provide some stirring. And so this is one of the processes through which stars can impact their surrounding environments, and we call this feedback. There's other feedback processes. For example, stars shine light into space, as we all know. And if we look at these pillars of creation and zoom into one of the pillars, we can literally see the pillars evaporating, right? That looks like the pillar is evaporating. because it is evaporating. It's evaporating because outside of this frame, somewhere up there, there is a very bright, massive star that's shining on these pillars. So the intense radiation from this massive star is causing the pillar to evaporate. And most importantly, perhaps most importantly, stars, the massive ones, can explode when they die as supernovae. So here is a famous example called the Crab Nebula. This was created about 1,000 years ago by a supernova. And that supernova was recorded by the Chinese astronomers in, I think, the Song Dynasty. Interestingly, it wasn't recorded in Europe because the Europeans were too busy doing medieval things. And that explosion created this beautiful nebula and also left a pulsar in the center. And we can still see the effect of this explosion that happened 1,000 years ago. And so these days, what we think happens inside a galaxy is that there is an interplay between gravity and stellar feedback so that stars form slowly rather than very rapidly. So I'm going to show you a movie from a numerical simulation done by my friend Miao Li. This is showing just a small part of our Milky Way. The disk is in the center. This is just a small part of the Milky Way disk. And as you can see, these supernova explosions will destroy cold dense gas and also create outflows. And all of these will slow down star formation. And we can also look at individual molecular clouds. And instead of turning all of the gas into stars, you can see that at the beginning, some of the gas form stars, but then very quickly, the big stars go supernova. I'm going to show it again. The big stars go supernova, and the supernova explosion destroys the rest of the gas so that it can't form stars anymore. And that's why we think that's why star formation is very inefficient in galaxies. So now I'm going to talk a little bit about my recent work related to star formation and turbulence in the interstellar medium. So I was looking at the Orion complex. I hope most of you know where the Orion constellation is, or you can find the Orion constellation. So these are the shoulders, and these are the three stars in the belt. These are the 2 feet. And many of you probably have seen this beautiful picture of the Orion Nebula. This Orion Nebula is somewhere in I think the dagger of Orion. And on a very clear night, you can even see this nebula with naked eyes. So it won't look this pretty, but you will see a fuzzy blob there. So that's this Orion Nebula. And this red part is showing, so this is a composite image. The red is H alpha. H alpha is a Balmer line. So this is coming from ionized hydrogen. And when you see H alpha, you know that something must have excited the hydrogen. So this is excited hydrogen atoms. And we call this thing Barner's loop. And we think that this was created by a supernova explosion that happened maybe 4 to 6 million years ago. Okay, now we think that the interstellar medium is turbulent, but how do we know that it's turbulent? And what is turbulence anyways? I still haven't quite explained what is turbulence. Like I said, we we don't have a complete description of turbulence. So if you ask 100 physicists, they'll probably give you 100 different answers as to what exactly is turbulence. But I think most of us would agree that one important characteristic of turbulence is the energy cascade, meaning energy is always going from big whirls to little whirls in three-dimensional turbulent flows. Just like the poem described, big whirls have little whirls which feed on their velocity, and little whirls have lesser whirls, and so on to viscosity. And one can work out that in a steady state turbulent flow, where you keep injecting energy on the largest scales, stirring up, for example, the water at the largest scales, then constantly these big whirls and twirls and eddies will turn into little whirls and smaller whirls. And there should be a relation that describes the characteristic velocities of a whirl and the characteristic size of a whirl, such that bigger whirls move faster and smaller whirls move more slowly. And in 1981, a famous astronomer, Larsen, discovered the famous Larsen's law for the interstellar medium, where he was looking at the relation between the sizes of clouds in the interstellar medium and their characteristic velocities. And he found that there is this beautiful relation between the sizes of clouds and the velocities of clouds on the y-axis. So basically, bigger clouds move faster, smaller clouds move more slowly. And this is consistent with what you would expect from a steady state turbulent flow. And this is still a very important piece of evidence that the interstellar medium is turbulent. Now, it's not always easy to observe gas, and there's always an issue with observations of gas, because if you look at the picture on the left-hand side, look at the gas, you are only looking at projected information. So we don't know exactly where the gas is located. And we also can't really see how the gas is moving across the plane of the sky. We can only probe the line of sight velocities of the gas. And I had this thought or idea, if we think that stars form out of these clouds in the interstellar medium, and these clouds are turbulent, wouldn't newly formed stars still carry some of that memory of turbulence from their parent clouds? And the wonderful thing about stars is that these days we have the Gaia survey and the Apogee survey, and when we combine them, we actually get 6-dimensional information of some of the nearby stars in our galaxy. What does that mean? 6-dimensional information of stars. We know exactly where they're located in the 3-dimensional space. We also know exactly how they're moving. So we know there's 3-dimensional velocity. And if we can show that the young stars are probing turbulence, then we can really probe the 3-dimensional turbulence for the first time. And so the picture on the right-hand side was made by my collaborator, Marina Kunkel, showing the stars she had analyzed with her data. And when I showed this to an artist friend, he said, "Wow, that looks like ocean current." And I said, "Yes, because I think we are seeing turbulence here, traced by stars." But you have to prove that, right? It's not immediately clear by looking at this picture whether these stars are following a turbulent flow pattern or they're just moving randomly like kids on a playground. So we carefully selected some stars that are really, really well observed here. And we also sorted them into separate groups depending on their age and location, etc. So they're classified into Orion A, B, C, D, and Lambda Orion. There's also a star group called ONC, Orion Nebula Cluster, and I'll come back to that cluster in a little bit. Actually, in the next slide. All right, so we analyzed the motions of these stars, and we computed their velocity structure function. So it's similar to what I just talked about in Larson's law. It's basically the relation between separations of stars, physical separations of stars, and their velocity differences. So it's probing the same kind of size velocity relation. And what we see is that for all these loose groups in Orion, from A, B, C, D, and lambda to lambda Orion, we see a relation that is consistent with the expectation of a turbulent flow, and also generally consistent with Larson's law for gas in the interstellar medium. So Larson's law is shown in blue. There's one exception, which is this ONC, the star cluster here, this yellow dot. There, you can see that this line is more or less flat. And that is because ONC is a very dense star cluster. And so there's a lot of gravitational interactions between stars within a dense cluster, which has erased the memory of turbulence. And so here, we're really mostly looking at random motions rather than turbulence. So we're no longer seeing this beautiful power law. So what we have confirmed is that indeed one can use stars, young stars, to trace turbulence in the interstellar medium. And so after we did this work, we applied the same method to a few more star-forming regions in the Milky Way. So now we have also included Ophiuchus and Taurus and Perseus. So what we see is that just like Orion, all of these star-forming regions follow the same kind of universal turbulence. And so these different colors are representing different stellar groups. And we've also looked at turbulence traced by stars compared with turbulence traced by gas. So we looked at the H alpha gas. And just to remind you, H alpha is coming from ionized hydrogen. And here we find something quite interesting. So in some groups, like in Orion and Ophiuchus, the turbulence traced by H alpha has a higher amplitude than turbulence traced by stars. But in Perseus and Taurus, they're either consistent with each other, or H alpha is actually a little bit lower than what's traced by stars. And what we think is happening is that, well, we know that the difference is the difference between Orion and Ophiuchus and these two other clouds is that in both Orion and Ophiuchus, there has been recent supernova explosions. So what we think is happening is that the supernova explosion put a lot of energy into the H alpha gas, but that energy has not been shared with the other phases of the interstellar medium yet. So if you're looking at a region where there has been a recent supernova explosion, then the H alpha would have the highest level of turbulence. So it's kind of like when you're pouring water into your teacup, you're just stirring up the water and the tea leaves follow. And that also shows the complexity or the extra level of complexity of astrophysical turbulence. And that is, you have different phases of the interstellar medium. And these different phases can have different levels of turbulence. Another complexity of interstellar turbulence is there are also magnetic fields everywhere in the universe. So here is not a painting by Van Gogh, but it's real data from Planck showing us the magnetic field structures of our own galaxy. And what's in the middle is our Milky Way disk. And if you zoom into a star-forming region, for example, the Orion Nebula, you also see very complex magnetic field structures. And from theoretical and numerical studies, we already know that magnetic fields can modify the behavior of turbulent flows. So we really hope that in the future, when we have more data, better data on the stars, we'll be able to use these young stars to probe the three-dimensional structure of magnetic fields in the interstellar medium. Okay, so to summarize, turbulence is everywhere in the universe. Inside galaxies, the motions of gas and young stars are both turbulent. And supernova explosions first inject energy into the warm ionized gas in the interstellar medium. And lastly, astrophysical turbulence is very complex, but also very cool. Okay, so I think I still have some time to do a quick advertisement for UNT. So I'm an assistant professor at UNT, and it's University of North Texas. It's located very close to Dallas. The college town is called Denton. I think it's a very lovely town. And we have a physics department with a PhD program. We have some good people looking for students and postdocs. So I would encourage people who are interested in going to graduate school or getting postdoc positions to consider looking at the research that's done at UNT. Okay, thank you.
Great, thank you so much. It's really, really exciting. Really exciting results.
Thank you.
And I have questions, but I'll let our audience ask first. So anybody on Zoom here would like to ask a question? Don't be shy, or if you are too shy, you can type your answer, your question in the chat. Okay, let me ask one. Let me use my privilege as a host to ask one. So for H alpha, were you able to get 3D velocity or just 1D?
Just the line of sight velocity.
Yeah, and then is that enough information to actually get to get
yeah, so it's not ideal if the gas is distributed in a very thin sheet, then it doesn't matter. Right. But if it's and we know that it's most likely not just within a thin sheet. Yeah. So there is a projection effect. Yeah. I guess there's not really a good way to correct for that unless we can figure out where exactly the H alpha is located. But for now, we can only say that given what we know about projection effects, these slopes would be flatter than the real slopes. Yeah.
Yeah, I guess we probably need some simulations for those projection effects.
Yeah. So we've seen some experiments done by other groups before. So like I didn't get to mention. So the pink lines are from a a previous study on the molecular gas, the very, very dense molecular gas by Qian et al. And they actually did look into the projection effect using some numerical simulations. What they were showing, and you can see here as well, is that when you have a thick cloud, basically the structure function gets flattened due to the projection effect. Yeah.
I see.
Yeah, but for some reason, H alpha still looks very steep.
Maybe you happen to have one that's like favorably aligned on the sky.
Yeah, I think well, I think there could also be maybe, I don't know if there's also seeing effect, but I don't think seeing. Yeah, that's the thing that I'm not quite sure about. It might be seeing effect.
I see.
Yeah, but
yeah, sorry, I was thinking
also probably
technical,
also supersonic turbulence. Yeah.
So we have a question here. What is the critical value for the Reynolds number in the heavens?
So the critical value for turbulence to occur, we think, is the same everywhere. So it's, I think, around 100, right? Maybe 80, I don't know. 100 is probably the critical Reynolds number for turbulence to occur. So it's so in this example, when it's 50, it's still mostly laminar flow. When it's 100, you can see some turbulent pattern. And in astrophysics, the Reynolds numbers are on the order of millions to billions or even higher. So it's very, very, very turbulent, or it can be very turbulent. So turbulence should be able to develop very, very easily. Yeah.
I see. Okay, great question. And any more questions here from okay, if I can use my privilege to ask one more, can you apply this your method to study Orion to, say, galaxies or galaxy clusters?
I did galaxy clusters first.
Yeah.
Yeah, I did clusters first.
You already did that. I just
Yes.
you just didn't show it.
Yeah.
That's really so cool. And how turbulent are galaxy clusters?
I have to say it's not conclusive. Maybe we should chat off the line, because yes,
yeah.
You would be, yeah, you would find it very interesting. So similar to what you see here for the H alpha. So I was basically analyzing the H alpha filaments in galaxy clusters. And you would think that with the projection effect, you would see a flatter spectrum. Instead, we were seeing something actually very similar to what you see here, which is steeper than Kolmogorov power spectrum. And now in this case, in Orion, it looks like it's more or less consistent with supersonic turbulence, right? But in galaxy clusters, so far we've looked at 3. One of them is consistent with half. The other 2 are even steeper than that. So it's very bizarre. We we don't have any explanation that everybody likes. So we just provided all kinds of possibilities, including plasma physics, plasma instabilities, right? Or magnetic fields. You just blame magnetic fields. But I really think that it's just like in Orion and Ophiuchus, we're seeing a lot of the behaviors of the driver itself instead of the cascade. Well, but right now I can't prove that yet. But if that's the interpretation, then that would mean there's very little amount of turbulence, actually. or a very small amount of kinetic energy cascades down to smaller scales. So if I think I know what you're thinking, then you're wondering about the level of turbulent dissipation, right? Or turbulent heating. And I would say it's small, but it depends on the interpretation of the results.
Yeah. So Justin, would you like to ask your question?
Okay. Can a turbulence model scale mathematically from small?
Oh, maybe Justin will say there. Yeah.
The same. So yes. Wait. Are you wondering? So as long as fluid description can still apply, and as long as magnetic fields are not fundamentally changing the behavior of the fluids, then yes. Or if you're describing fluids that are magnetized to the same level, then it shouldn't matter what kind of scale you're looking at. It would be the same set of equations or the same statistical relations. Now, maybe I don't know if that's what you're thinking about, or you're thinking about the sort of exotic astrophysical environments being no longer it's no longer a fluid. That's what you're thinking about.
No, I think it's fascinating, Dr. Lee, that you've got this this phenomenon that you can model from something you can hold in the palm of your hand to, you know, a cosmic scale, really. But even so, it's so complex that it's incredibly difficult to sort out. And like you said, there certainly would be a lot of other things like magnetic fields, but I guess the fundamentals, I was just going to ask, would the fundamentals then be the same? I mean, if you removed other potential variables like magnetic fields or, you know, too much cream in your coffee, for example, or something like that, it would still be the same. That's fascinating.
Well, yeah, like, thank you. That's a good question. So yeah, so if we can show that fluid approximation is still good for astrophysical fluids, then yes. But we're not sure about that assumption because, you know, I was cheating a little bit earlier, right? If you look at, even if you just look at fire is not gas anymore. This is plasma, right? And so is the surface of our sun or the solar wind. And the funky thing about plasma is there are additional plasma instabilities, or, you know, just interactions between particles and waves and magnetic fields in very, very complex ways. And we sort of understand some of these plasma instabilities on small scales. And when I say small scales, I'm talking about the gyro scales of electrons, for example. And in the context of a galaxy, that would be sort of the size of the solar system, maybe. So that's the small scale, right, astrophysically. And that is much smaller than the scales we can typically probe, right? When we're looking at a galaxy, we're looking at many light year scales. And so how the very small scale plasma physics affects the behavior of fluid on larger scales is a big unknown. And there are a lot of people working really hard to try to figure that out. But because of the sheer scale difference, it's really hard to connect these different scales. And we can only hope that the plasma instabilities are helping make the astrophysical fluid a fluid. rather than something that we just don't understand. But yeah, we are thinking about whether or not it is the same kind of fluid that we think we understand, or we think that we can study on this planet with a coffee mug, right? Yeah.
Well, it's a fascinating problem. Thank you very much for this fascinating talk. This is very
Thank you.
interesting.
Titus, would you like to ask your question directly?
Okay, so I'm just quite curious because now we know that the turbulence within a galaxy affects the star formations that happen within the galaxy. So, and then you also did mention that stars are being formed, but rather more inefficiently. So I just want to know if the galaxies would have exhibited a different behavior than what we see now, if the stars were being formed more efficiently.
Yes, and we do think that there are galaxies that are forming stars more efficiently, and there are some that are forming stars less efficiently. And we're trying to understand why there is a difference. If that answers your question. So there is a scatter in the star forming efficiency across different galaxies. But the one thing we know for sure is that they're all inefficient. Maybe except the very, 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 very bursty, intense star forming galaxies where the efficiency is maybe close to 100%. But in the vast majority of galaxies, star formation is happening sort of slowly and steadily.
Yeah, that's really an active area of research. Yeah, great question, Titus.
Yeah.
So we like we know there's turbulence everywhere, like all over. And I'm also quite curious. I don't know if this turbulence is playing a major role in keeping our universe balanced as it is now, or maybe if there was no turbulence in the universe at all, it would be much more stable.
Kind of philosophical, actually.
Yes, that's a very interesting question. Yeah, it's yeah, that's really interesting to think about. Yeah, but yeah, I'll also add that it's not, turbulence is not just regulating star formation within the disk. One can argue that it's also regulating star formation from a larger scale. So I think I had the slide but got rid of it later on. I had this movie, right, showing the winds driven by supernova feedback. So we've also observed these winds coming out of galaxies, and we think that these winds are also creating larger scale turbulent flows within the whole galactic halo. And that also maybe provides some regulation to star formation on the larger scales.
Okay.
Yeah, great question. Any more questions? Okay. If there's no more questions, let's thank Dr. Lee again, and thank you so much for a great talk.
Thank you so much for having me.
Yeah, thank you everyone in the audience.